All right, now we want to talk about upper and lower sums. The procedure used in example 3 can be generalized as follows. Consider a plane region bounded above by the graph of a non-negative continuous function y equals f of x, like this one. Notice from A to B, it's all above the x-axis and it's continuous. The region is bounded below by the x-axis, and the left and right boundaries of the region are the vertical lines x equals a and x equals b. To approximate the area of the region, begin by subdividing the interval a to b into n subintervals, each of which delta x equals b minus a divided by n. So what's that? B minus a divided by n? Well, b minus a is the width of the entire region. N would be how many subintervals you're dividing it into. Like if you're dividing it into 10 different rectangles, then you would do b minus a divided by 10. That's going to be your delta x. That's how much the change in x is. That's the width of each little subinterval. Okay? The endpoints of the intervals are as follows. So the left endpoint of the first rectangle is just going to be a. But in terms of delta x, it'd be a plus 0 times your change in x. The next one would be a plus 1 times change in x. The next one would be a plus 2 times delta x. And the last one would be a plus n times delta x. Because f is continuous, the extreme value theorem guarantees the existence of a minimum and maximum value of f of x in each subinterval. So f of mi would be the minimum value, f of capital Mi would be the max value. Next, define an inscribed rectangle lying inside the ith subregion and the circumscribed rectangle extending outside the ith subregion. The height of the ith inscribed rectangle is f of mi, and the height of the ith circumscribed rectangle is f of capital Mi. For each I, the area of the inscribed rectangle is less than or equal to the area of the circumscribed rectangle. So the area of the inscribed rectangle equals f of mi times delta x, which is less than f of capital Mi delta x, which equals the area of the circumscribed rectangle. The sum of the areas of the inscribed rectangles is called the lower sum, and the sum of the areas of the circumscribed rectangles is called an upper sum. So the lower sum equals lowercase s sub n, which is equal to the sum I equals 1 to n of f of lowercase mi delta x. That's the area of the inscribed rectangles. And the upper sum is capital S of n, which is the sum I equals 1 to n of f of capital Mi delta x. That's the area of the circumscribed rectangles. So from this figure, you can see that the lower sum is less than or equal to the upper sum. Moreover, the actual area of the region lies between the sums between these two sums. In other words, the area of the region is between the under approximation and the over approximation. Kind of makes sense, huh? So find the upper and lower sums for the region bounded by the graph of f of x equals x squared and the x-axis between 0 and 2. So begin with partition the interval into n subintervals, each with a width of b minus a over n. Well, b and a are 2 and 0, so the width of the entire region is 2 divided by the number of subintervals, which in general is n. So this figure shows the endpoints of the subintervals in several inscribed and circumscribed rectangles. In other words, this one they use left endpoints, and that makes them all inscribed because they're inside of the area region. These ones are circumscribed because they stick out over the region, and these are all right endpoint rectangles. Because f is increasing on the interval, the minimum value on each subinterval occurs at the left endpoint, and the max value occurs at the right endpoint. So the left endpoints are 0 plus I minus 1 times 2 over n, which is 2 times I minus 1 over n. The right endpoints would be 0 plus I times 2 over n, which is 2i over n. So right endpoints, you're just going to, whatever your beginning part of your entire interval is, in this case it was 0, but if you went from like 1 to 3, this would have been a 1. Then you do plus I times whatever your delta x is. If you're doing left endpoints, same thing, except you, instead of multiplying by I, you multiply by I minus 1, which shifts you over to the left endpoint. Okay? Using the left endpoints, the lower sum is the sum of f of mi delta x, which is f of this right here, times delta x, which we figured out was 2 over n. Remember, the function was x squared, so we plug this in as your x. So it's that squared times 2 over n. Now, if you simplify this out, like you're going to square this and distribute. So if I square this, you have 4 times I minus 1 squared over n squared. If I have I minus 1 squared, that's I minus 1 times I minus 1, which would give you 4 times I squared minus 2I plus 1. Okay? And then we simplify a little bit more, and you have I squared minus 2I plus 1. Then you could factor an 8 out of everything and divide by n cubed. Where'd the n cubed come from? Remember when I squared this n right here, it became n squared from the square here? Well, if you multiply this n, you would also have, then you would get n cubed. Where'd the 8 come from? Well, this 2 squared is 4 times this 2 gives us the 8. Okay? The 8 over n cubed is a constant because the index of summation is considered the variable. All other letters are considered constant, so I can factor that out. And since these terms are just added and subtracted, I can add or subtract their sums. Since this is 2 times I can factor out the 2. Then the next step is just to use the summation formulas for I squared, for I, and for a constant. So it's going to be 8 over n cubed times the summation formula for I squared minus twice the summation formula for I plus the summation formula for the constant 1. Okay, now after some nifty algebra, like you FOIL all this out, FOIL this out, distribute the 2, and then get a common denominator for everything and add it all together and factor out common factors, you get 4 over 3n cubed times the quantity 2n cubed minus 3n squared plus n. If I distribute this 4 over 3n cubed here, here, and here, you would get 8/3 minus 4 over n plus 4 over 3n squared. That's the formula for the lower sum. Similarly, with right endpoints, this is going to work out a little bit easier because here I didn't have the I minus 1, it just had an I. So it's going to be that squared because the function was x squared. If the function was like x cubed minus 4x squared plus 6x times 3, well, you'd have to plug this 2I over n in for each of those x's and simplify from there. So you square that, factor out the 8 over n cubed, use the summation formula for I squared. FOIL all that out, get your common factors, distribute, and then you get your lower upper sum right there. So example 4 illustrates some important things about our lower and upper sums. First, notice that for any value of n, the lower sum is less than or equal to the upper sum. Second, the difference between these two sums lessens as n increases. Remember, n is the number of subdivisions, so it's the number of rectangles. As the number of rectangles increases, you have to squeeze more rectangles into that region so they're going to get thinner, so you're going to get a better and better approximation of the area under the curve. So the amount that the circumscribed rectangles is an over approximation is going to get smaller, and the amount that the inscribed rectangles are an under approximation is also going to get smaller. So the difference between the two is going to get smaller as well. In fact, if you take the limit as n approaches infinity, both the upper and lower sums should approach the same value, and in this case, both of them would approach 8/3. If you let this one go to infinity, these two terms would go to 0, and you just get 8/3. And same thing would happen with these ones as well, and you would just get 8/3 there. Okay, so the limit of the sum is 8/3. The next theorem shows that the equivalence of the limits as n approaches infinity of the upper and lower sums is not mere coincidence. It is true for all functions that are continuous and non-negative on a closed interval. So this is the limit of the lower and upper sums theorem. Let f be continuous and non-negative on the interval a to b. The limits as n approach infinity of both the lower and upper sums exist and are equal to each other. In other words, the limit of the lower sum is equal to the limit of the upper sum. Now remember, delta x is the width of the entire region divided by the number of subintervals. And f of mi and f of capital Mi are the minimum and maximum values of f on the subinterval. Because the same limit is attained for both the minimum value and the maximum value, it follows from the squeeze theorem that the choice of x in the ith subinterval does not affect the limit. This means that you're free to choose any arbitrary x value in the ith subinterval, as the following definition of the area of a plane region indicates. Let f be continuous and non-negative on the closed interval a to b. The area of the region bounded by the graph of f, the x-axis and the vertical lines x equals a and x equals b, is equal to the limit as n approaches infinity of the sum of I equals 1 to n of f of ci delta x, where ci is somewhere in between x of I minus 1 x sub I, and delta x is b minus a over n. So somewhere in that interval. Okay, it could be the left endpoint, could be the right point, could be the midpoint, could be somewhere else. All right, so let's find the area by limit definition of x cubed, the x-axis, and the vertical lines x equals 0 and 1. So here's the graph of x cubed. We go from 0 to 1, and we want this pink region. Okay, we just drew a representative rectangle in there. So begin by noting that f is continuous and non-negative on the interval 0 to 1. Next, partition the interval into n subintervals. So b minus a over n would be 1 minus 0 over n, which is 1 over n. So our delta x is 1 over n. So you could choose any x value in the ith subinterval. For this example, and most examples, it's going to be easiest if you pick right endpoints. Okay? So the right endpoint is just I over n. That's it. Pretty much the right endpoint is I times delta x. It's pretty much what the right endpoint's always going to be. Okay? So that's how we got I over n, because it'd be I times 1 over n, which is I over n. So the limit, so area is the limit of the sum of f of ci. So I'm going to plug this I over n into the function and multiply by my delta x. So it's I over n cubed times 1 over n. So if I cube this, I'd get I cubed over n cubed times 1 over n, which would give me I cubed over n to the 4th. I is the index of summation, so I is the variable, n is considered a constant. So I can factor the 1 over n out and do the sum of I cubed. I know a summation formula for I cubed. There it is. Okay. So you got rid of the sum and substitute it with its summation formula. Now I can just algebraically simplify this a little bit. Okay, the n squared and the n to the 4th would just reduce that n to the 4th to an n squared. Then I would FOIL this out, break it up into separate fractions over fourths, distribute the n squared to the denominator, and cancel like terms, or common factors in the numerator and denominator rather. And you get this. Now if I take the limit as n approaches infinity, this term goes to 0, and this term goes to 0, and your limit is 1/4, which implies that the area of this region is 1/4. Pretty cool stuff there, huh? All right, let's do another one. Find the area of the region bounded by the graph of 4 minus x squared, the x-axis, and the vertical lines 1 and 2. So here we go. 1 and 2. So the function is continuous and non-negative on 1 to 2. So begin by partitioning the interval into n subintervals, each with delta x equals 1 over n. Again, b minus a over n. 2 minus 1 is 1. Over n is over n, so it's 1 over n. That's your delta x. That's the thickness of each rectangle. So the right endpoint, okay, is going to be, since it doesn't start at 0, you have to start at the beginning of the region. So it's going to be a, which is the right endpoint of the region, plus I times delta x. So the right endpoint of the entire, or the left endpoint of the entire region is 1, so it's going to be 1 plus I over n. Because you're starting at 1, and to get the right endpoints, the first endpoint is 1/nth over from that. So it's 1 plus 1 over n. Then the next one's going to be 2/nths over from that, so it's going to be 1 plus 2 over n, and so forth and so on. All right? So then you would substitute 1 plus I over n into this function, so it's 4 minus the quantity 1 plus I over n squared times delta x. Remember, this represents the height of each rectangle, and the 1 over n is our delta x, which represents the width. It's just area, base times height, width times height of each rectangle. The summation means you're going to get the area of each rectangle and then add them up. All right, so some handy dandy algebra here. If I FOIL this out and keep it in parentheses, you got to FOIL it out and then subtract each term. Get this right here. Okay, then I can factor this 1 over n out and break it up into 3 separate sums like this and factor out the constants from those. Remember, in the sum, the index of summation is I, so the variable is I, and n is held constant. So then if I plug in the summation formulas for a constant, for I, and for I squared, I get those. Simplify those algebraically and distribute these factors here. Then if I take the limit as n approaches infinity, this term, and this term all approach 0, and you get 3 minus 1 minus 1/3, which is 5/3. So that means the area of this region is just 5/3. Pretty cool, huh? All right, one last one. Let's look at what happens when we bound it by the y-axis. So find the area of the region bounded by the graph of f of y equals y squared. So y squared, f of y equals y squared, is a sideways opening parabola. And here, the boundaries are the graph, the horizontal lines at the endpoints of the interval, so at y equals 1 and y equals 0, and the y-axis. Okay, it's kind of like they flipped the graph over a little bit. So when f is continuous and non-negative function of y, you can still use the same basic procedure as in examples 5 and 6. So start by partitioning the interval 0, 1 into n subintervals. So b minus a over n, 1 minus 0 over n is 1/nth. Then using upper endpoints, you make your ci just I over n. And you don't have to add or subtract anything from it because the region starts at 0. Okay, so it's like 0 plus I over n, which is I over n. Then you just do the summation formula of f of y times delta y. Pretty much is all we're doing. F of y would give me like the length kind of, but it's really the height of the rectangle. Delta y is the thickness. So substitute in what you know. The function is y squared. The x value or the ci value is I over n. So it's going to be I over n squared times delta y, which we found to be 1 over n. So if I simplify that, I square this, factor out the 1 over n cubed, and you get 1 over n cubed, sum of I squared. Use the summation formula for I squared. Distribute everything out, break up the fractions. Now you can take the limit as n approaches infinity, you get 1/3. So the area of the region is 1/3. All right, guys, that's it for this section. Please continue on to your assignments. I know there was a lot in this section, a lot to cover, a lot to chew through, so please reach out to me if you have any questions whatsoever. Take care.